Okay, so I would like to start by thanking the organizers for this wonderful conference and for inviting me to speak. And this talk is based on work with Fernando Alday and Joao Silva. And we are motivated by the question how we can formulate string theory on curved backgrounds, or also string theory with Ramon backgrounds. Of course, this is a very hard question, so a more specific question is, can we at least do it for AdS5 CFT4? This is an amazing theory. It has been studied from many angles, but even after all these years, we still don't have a full worldsheet CFT. So how can we make progress? So the next question here is, what would Veneziano do? Probably he would try to fix the amplitude first, and so this is kind of our philosophy here. So this is the process we want to study, and we have the luxury that we have three different descriptions. We have in the bulk type 2B string theory on AdS5 process 5. On the boundary, and in the process we want to study is this genus 0 or tree level scattering of closed string gravitons. On the boundary we have n equals 4 super Young-Mills, and since we are interested in a weakly coupled string, we will take this in the planar limit. And then there should also be this unknown worldsheet CFT. So in this talk, we will content ourselves with just trying to fix the amplitude, and we will use a little bit all of these three perspectives on this process. So what is this AdS amplitude? We define it in terms of the conformal correlator of an operator O, which is the superconformal primary of the stress tensor multiplet in n equals 4 super Young-Mills. So it's related by supersymmetry to the stress tensor, and we will do a certain integral transform that I will describe in more detail later to arrive at what I call the AdS graviton amplitude. We will study this in a small curvature expansion where the expansion parameter is alpha prime divided by AdS radius r squared, or equivalently we have a expansion in inverse powers of the 't Hooft coupling. So I will use the terms small curvature expansion and strong coupling expansion interchangeably here. So the leading term in this expansion is the flat space Virasoro Shapiro amplitude, where St and U are Mandelstam variables in units of alpha prime. If you miss the graviton polarizations here, this is because I took out an overall factor that is fixed by supersymmetry. And A1 and A2 are the first two curvature corrections, and in this talk I will explain to you how we managed to fix them. So how can we fix them? So I made this shopping list of general properties of string amplitudes that we can use. And we have the partial wave expansion, Regge boundedness, and we have the existence of a worldsheet integral. And I will go shortly through this list and say a little bit about each of them. So first of all, we have the partial wave expansion. We know in flat space that if we study the resonances of the amplitude, we can extract the spectrum of exchanged massive string modes. So we have here this plot, the mass level delta versus the spin L, and we have this famous linear Regge trajectories. The analogous concept in AdS-CFT is the conformal partial wave expansion or conformal block expansion. And the AdS-CFT dictionary tells us that if we study the dimensions of these massive string modes at large AdS radius, the dimensions are given by radius times flat space mass. So we can use this relation down here to express this in terms of the mass level. And it was shown in this paper that the leading term, that in this theory there are indeed operators where the leading term of the dimensions is given by this. Later we learned from integrability that we can also compute these dimensions at finite radius or finite coupling. First for the leading Regge trajectory, which is shown here in red, and later also for other operators. The next thing is Regge boundedness. Of course, the amplitude for large S and fixed T goes like S to the T. And if we want to reconcile this with the partial wave expansion, where each partial wave goes like S to the spin L, this places strong bounds on the partial wave coefficients. So we will also use Reggie-boundedness to our advantage. It's a very strong constraint. And finally, we have the worldsheet integral. And as usual, we map the worldsheet conformally to a Riemann sphere with insertions at 0, z, 1, and infinity. And in flat space, we have this formula for the amplitude. So if there's a worldsheet theory, the curvature correction should also have a representation as an integral over the worldsheet. The only problem is we don't know the integrand, gk total, for the kth curvature correction. But we can learn a little bit how this integrand should look like by thinking about a nonlinear sigma model for AdS in a small curvature expansion. We can just take a bosonic toy model, and if we do this expansion, we see that we get something that looks like flat space amplitude with extra insertions of soft graviton vertex operators. So if we study this in detail, we see that this function should be expressible in terms of single-valued polylogs of weight 3k. Okay, so let's make a plan how we can fix the curvature corrections. We will attack the problem from two sides. First, we combine the conformal partial wave expansion with Reggie-boundedness to derive a CFT dispersion relation. This is an expression for the amplitude that depends on unknown data, the CFT data. On the other hand, we will make a single-valued ansatz for the worldsheet integrand. This also depends on unfixed coefficients. But by equating both expressions, it turns out we can fix all the coefficients, and we get the amplitude. Now we made some assumptions, so we need to do checks, and luckily there's a lot of data available. We can compare the dimensions of these massive string operators that are exchanged to results from integrability. We can compare the Wilson coefficients in the low energy expansion with results from supersymmetric localization. And finally, we can study the high energy limit and compare it to a classical computation a la Gross and Mende, but in AdS. Okay, so let's start with the CFT dispersion relation. As I told you, we have three perspectives on this process, and for each perspective, there is one observable. We have the function g associated to the worldsheet, a the AdS amplitude, and in the bottom left, we have the correlator. To go from the correlator to the AdS amplitude, we first do a Mellin transform, and then we do a certain Borel transform that was introduced by João Penedones as the flat space limit. He showed that in the strict flat space limit, this takes each Witten diagram to the corresponding flat space Feynman diagram. The new thing now that we are doing is we use the same thing for the curvature corrections. To be a bit more explicit, on the left I have the inverse Mellin transform. Here u and v are the conformal cross ratios, and gamma is a fixed prefactor. And what this does is it relates the poles of M to powers of cross ratios in the correlator. The Borel transform provides us with a Borel resummation of the low energy expansion of the Mellin amplitude. And there's also a rescaling of the variables by a factor square root of lambda here. So while A has poles at non-negative integer values of S and T, in the Mellin amplitudes, these poles get shifted towards infinity when we study the strong coupling limit. Next, we derive a dispersion relation. For this, we use that the Mellin amplitude has poles that all the poles of the Mellin amplitude are associated to the OPE. The location of the poles is given by the conformal dimension and the spin, and the residue contains the OPE coefficient squared and this polynomials Q, which are basically the Mellin transform of the conformal blocks. We also have Reggie-boundedness, which just says that in the Reggie limit, we should have a softer behavior than supergravity. And now we can just write M as a contour. So this is a fixed T dispersion relation, where we just write M as a contour integral around a pole, blow up the contour, pick up the S and U channel poles, and the arc at infinity vanishes because of Reggie-boundedness. So what are these operators that appear in this dispersion relation? The relevant operators are the massive string modes, And in n equals 4, this corresponds to unprotected single trace operators. And we will continue labeling them by the flat space quantum numbers, mass level, and spin. And we can go ahead and expand the OPE data in the strong coupling expansion. The leading terms will be completely fixed by the flat space amplitude. And then each curvature correction gives us more orders in the OPE data expansion. OK, so let's go back to the dispersion relation. We have now to go from the Mellon amplitude to the AdS amplitude. And we can do this transformation, expand around the pole, and see what pole structure this implies for the curvature corrections to the amplitude. What we get is we get a pole of order, for the kth curvature correction, we get a pole of order 3k plus 1. And the residue depends only on OPE data that is fixed by flat space. There are also lower order poles which depend on more and more of the corrections to the OPE data. So we learn from these two things. The OPE data at a given order fixes much of the pole structure of the next curvature correction. So this is promising because it means this is a powerful formula. On the other hand, we see that the worldsheet integrand should have transcendentality 3k. Because to get a pole of order 3k plus 1, we have to insert a logarithm to the power 3k into the integral. This is the second time that we are seeing this order 3k appearing. Previously, we saw it from the nonlinear sigma model argument. So now it's clear what to do. We should work order by order, write a worldsheet ansatz for the amplitude, compute this residue, and match with this pole structure, and see if we can fix the ansatz. But before we do this, we have to talk a little bit about the functions that we use for the ansatz. We start by introducing multiple polylogarithms. These are defined as iterated integrals with this integrand that has poles. And since we inserted the vertex operators at 0, z, 1, and infinity, the relevant poles can be or the poles that are relevant here are, we have labels zi equals 0 or 1. The properties of these functions are they satisfy this differential relation. W here stands for word, so this can be a sequence of letters, zeros or ones. These are multivalued functions. They are holomorphic. And if we evaluate them at z equals 1, we get multiple zeta values. Two examples are here. If all the labels are 1s, we get a power of log of 1 minus z. If we take a bunch of zeros and a 1, we get the classical polylogarithms. Now, the single-valued version of these functions was constructed by Francis Brown, and they can always be written as this weight-preserving combination of holomorphic and anti-holomorphic multiple polylogs. The coefficients c here are fixed if you demand that they have to satisfy the same holomorphic differential relation as the usual multiple polylogs, and that they are single-valued functions, most importantly. What we get now are functions that are non-holomorphic, and if we evaluate them at z equals 1, this is the definition of single-valued multiple zeta values. These form a subset of the usual multiple zeta values, and they're quite interesting because whenever you do a computation and you get only single-valued multiple zeta values, this is usually a hint that there's something single-valued going on. The examples here are analogous to the previous ones. So if we just have all the labels are 1, we get the logged power of log, but the argument is now an absolute value squared. And the other example is the single-valued version of the d logarithm. Note that it's not symmetric under exchange of z and z bar. So now we are ready to make our ansatz. We know it has to be crossing symmetric, so we write it as a sum of these three terms. And each of the term has this worldsheet integral representation. We will further assume that the integrand has transcendental weight 3k made out of single-valued multiple polylogs and single-valued multiple zeta values. And using dimensional analysis of and what we know about the low energy expansion, we can also infer that it should be a homogeneous degree 2k polynomial in S and T. Finally, full crossing symmetry demands that the functions are symmetric under simultaneous exchange of S and T and Z and 1 minus Z. Okay, so we make our first ansatz. The first ansatz has 11 rational parameters, and we demand consistency with the dispersion relation, and this fixes all the coefficients. We have a function of weight 3. Zeta 3 here is an example of a single-valued multiple zeta value. It's also a degree 2 polynomial, and yeah, that's it. The second correction, or the second ansatz, has 115 parameters, and 113 of these are fixed by the dispersion relation. The final two coefficients can be fixed by knowing the dimension of a single operator, for example, Konishi. So this is now weight 6 and the degree 4 polynomial. And we use this symmetrized version of the polylogs to make it explicitly crossing symmetric. Okay, so we made some pretty wild assumptions. So luckily, we have a lot of data to do checks. The first check is regarding the OPE data. From the result, we can extract all this OPE data in the 3 boxes. And in particular, we get this result for the leading Regge trajectory. So remember that delta is the mass level, and because we pick a Regge trajectory, the spin is also fixed. And this agrees precisely with the result from integrability. The next check is the low energy expansion. So this is the small S&T expansion of the amplitude, which makes contact with the low energy effective action, sucra plus quartic interactions with derivatives. So the expression looks like this. We have a sucra contribution and then just crossing symmetric polynomials in the Mandelstam's. And we can write this out and identify for each term to which interaction it belongs. Now all the alpha zeros are already fixed from flat space, and our result fixes all the alpha 1s and all the alpha 2s. Of these 4 values written here were already previously known from localization, and we get a match. After doing the check, we can go ahead and combine our results with localization to also completely fix the d to the 8 r to the 4 and d to the 10 r to the 4 terms, which are not protected by any non-renormalization theorems. The final check is the high energy limit, and here we generalize the famous work of Gross and Mende to AdS in a small curvature expansion. And they argued that the exponential behavior of the amplitude in the high energy limit is universal, so it depends only on a classical bosonic solution, so it's the same for the superstring and bosonic string. So we can just study this, this bosonic action here. It's a generalization of the one studied by Gross and Mende, where lambda is a Lagrange multiplier, ensuring that x is an embedding coordinate for AdS, and the 4 terms with the delta functions are the exponents of the 4 vertex operators. So we can find this classical solution for x, plug it back into the action, and get the right side here. The left-hand side is our result in the limit where we take s, t, and r to infinity all at the same rate. And we can compute this by saddle point. The saddle point is at z equals s over s plus t, and we get a match. This also means that the solution in the high energy limit is given by the high energy limit of flat space, which I didn't write here, and then the correction is an exponential function where the exponent is the first integrand at the saddle point. And we can check this exponentiation at quadratic order because we have the second correction. So at the saddle point, the second correction equals precisely 1/2 the square of the first correction. So both these sides here are huge expressions with weight 6 polylogs. Okay, so let me sum up what we did so far. So we combined the conformal partial wave expansion with Regge boundedness to derive a CFT dispersion relation. We combined this with a single-valued ansatz for the worldsheet integral. And we got the AdS Virasoro Shapiro amplitude in a small curvature expansion. As we saw by discussing the checks, this gives a very nice relation between bootstrap, integrability, localization, and a classical computation for the high energy limit. And there's one more thing. What about open strings? We can study a similar model where we include now 7 branes where open strings can end. So these 7 branes are fill up the AdS5 and the S3 inside the S5. And this is dual to a 4-dimensional n=2 superconformal field theory. And in this case, we also managed to fix the first 2 curvature corrections for the color-ordered gluon amplitude. So the leading term in this case is precisely the flat space Veneziano amplitude. And interestingly, the curve, like these integrands, G1 and G2, are still expressed in terms of single-valued multiple polylogs. This is because it's still curvature corrections, so it still can be thought of as coming from gravitons. Now, famously, the low-energy expansion of the Veneziano amplitude contains non-single-valued multiple zeta values, but this is just because of this final one-dimensional integral. One-dimensional integrals don't give single-valued things. Okay, so here are some future directions. We are working on doing the same for type 2a string theory on AdS4 cross CP3, which is dual to ABGM theory and the 't Hooft limit. We are also thinking about going beyond small curvature expansions and trying to find something at finite coupling. And I hope that eventually we can compute AdS string amplitudes directly from string theory. As we heard on Tuesday from Minjae's talk, apparently they have all the ingredients to do this computation from string field theory. Thank you.
Yeah, thank you for the very impressive talk and finishing early. Questions? Sasha?
Thanks. Could you comment on higher order corrections you just discussed too? What will happen if you go further?
Yes.
How much information you need?
Yes, so for the Virasoro Shapiro case, we would have weight 9 functions, and I think the answers would have around 1,000 coefficients. And we saw that we needed for the second correction a little bit input from integrability, but we haven't tried it yet.
So did you see any relation between this, like a G open and then G closed?
In the high energy limit, yes, because this is as expected. So in the high energy limit, the open string exponent is half of that of the closed string exponent. This is also a nice check for the open string case. But beyond that, not really, because these are also different theories. And the factorization of vertex operators, as we have in flat space, is not expected in AdS. Also, the integrand for the Virasoro Shapiro case, which has maximal supersymmetry, this integrand has uniform transcendentality. But for the open string, where we have only n=2 supersymmetry, it's not uniform transcendentality. It is also kind of expected.
Yeah,
So you showed this very nice representation that of the amplitude that works in this strong coupling expansion. Do you also get something, this representation also works at weak coupling? Does it also give something interesting there?
Yeah, the problem is that when we do the Borel transform, we also rescale the Mandelstam with the lambda. So it looks like when you do this at weak coupling, different loop orders mix. So if you have a finite number of loop corrections, it's not clear if this is enough to use this representation.
But you expect it to work at finite lambda?
Yeah, yes, I guess.
Yeah, please.
About the high energy limit, can it be extended to endpoint functions and include one of GS corrections?
I think so. I mean, finding this solution, yeah, it's related to the scattering equation. So finding these saddle points for higher point functions, one probably has to study the higher point
Yeah, you displayed this expansion of the dimension and powers of 1 over root lambda to a few others, but now there are some more known, like there was 2 days ago a paper by Gromov. And
Yes.
does it match that too? Or?
We just did the first 2 corrections, so if we would do another one, we could now use that paper to compare.
I see. So you can improve it. Any more questions? Yes.
Yeah, hi. Thanks very much for the talk. I just have a question about the polylogarithm. So the mathematicians know about a very rich structure of relations between them. So I was wondering whether you're using these relations in your analysis.
Yeah, we have to use the full power of single-valued multiple polylogs, like to show that, for example, if you want to square G1 here, you use shuffle relations to write everything in terms of weight 6 polylogs.
I see. So you're using all of them?
Yes.
Okay, thanks.
So you talked about doing it for ABJM, but have you thought about the D1, D5 CFT for AdS3? What can be done there?
Yeah, I haven't thought about it. As long as we have a weakly coupled string theory where we have a genus 0 amplitude, I think it should be a similar story. Yeah.
Thanks.
Okay, let's thank Tobias again for a great result.